Hello, everyone. Welcome to the next meetup organized by quantum computing groups from Washington, D.C., Toronto, and Warsaw. My name is Pawel, and I'll be the moderator today. And today we have pleasure to host a great speaker, Dr. Jarek Duda from Jagiellonian University in Kraków, in Poland. And he will present an idea for a two-way quantum computer by adding postparation as a reserved state preparation process to attack NP problems. A very interesting topic. So before we start, just a few announcements. So as you can see, this meeting is recorded. So hopefully the video will be later available on our YouTube channel. And we've agreed with Jarek that this meeting can be interactive. So if you have any questions, you can raise your hand and we'll try to interrupt, but you can also post your questions on the chat and we can ask in the Q&A session at the end. We would also like to announce our next meetup. So in 2 weeks from now, Terry Bollinger, who is with us today, will tell about fairy dust in physics, how non-physical views of information impede theory progress. And then on March, Eric Reiter will tell about a serious challenge to quantum mechanics. This will be part 4 of Eric's lectures. And finally, I would like to thank our partners and sponsors for helping us and in organizing these events. Good. So I will now stop sharing my screen. And Jarek, first of all, thanks for accepting our invitation. And if you are ready, the Zoom is yours and we can start.
Okay, thank you very much for this opportunity. So please interrupt me. You can discuss on the go. So the most important are first slide. So then there will be some more physics. Okay, so the main topic here is improving quantum computers. Yes, some standard one-way quantum computer looks like here. That we have state preparation, then some unitary evolution, and then measurement of usually of all the qubits. So in two-way quantum computers, we we add this postparation, which acts the same as preparation, but it's this symmetric version. So in CPT symmetric physics, having this state preparation, we should also have this symmetric version postparation, which in practice will act as a post-selection, but with higher success rate. So I try to convince that from physics perspective, it should be doable. So that I will show a few approaches how to, in theory, should be done, but I will gladly we could collaborate to maybe make it work. But so it's difficult experimentally, but in theory it should work, especially if you assume that CPT symmetry of physics is right. And show some properties. There are some articles. We have some group working in this topic. So if you are interested, we can have a Discord channel and generally we have group for X prize. So one approach is that, for example, for silicon quantum dots, we prepare a state as by tunneling electrons into these dots, silicon dots, by impulse. So performing opposite impulse at the end, and from perspective of CPT symmetry, we should get the original state preparation. Yeah, so we get the original impulse for the state preparation. So we just have to perform the reverse process used for state preparation. Yeah, so we have this kind of formulation that we have some initial state, final state, and unitary evolution between them. In CPT perspective, we switch the initial and final states, and we perform the conjugation of the unitary evolution. So in theory, physics allows to see the such process from both directions. Yeah, so past and future. So we just need to reverse the process used for state preparation. And one approach us here is that this state preparation process sometimes is just applied impulse, lack of potential. So we just need to use a reverse impulse. Yeah, so just reverse the shape of the used impulse, and from perspective of CPT symmetry, you should get the original state preparation process. This is one approach. So another approach is that in superconductors, one of approach for the state preparation, yes, there are lots of these. One of approaches of the state preparation is that it just uses a very low temperature. Yeah, so we have this very low temperature, so we can assume that everything is the ground state. However, so the temperature is does not change under the CPT symmetry, yes, because temperature is mean kinetic energy, so it's the same from CPT perspective. So in CPT perspective, this low temperature is still low temperature. There are still ground state atoms, yeah. So we have so this we shouldn't see them as just preparation, but also this symmetric version, this postparation, yeah. So lowering temperature is both preparation and postparation, in fact. So we can think about this kind of top simple situations. Yeah. So for example, if you have this situation, just knot and measurement, and from CPT perspective, this is the reversed. Yes, but what this is more interesting example of two-way quantum computer that we do not measure this qubit. So from CPT perspective, we just have ground state qubit which enters this unitary evolution. So it should act as a state preparation. Yeah. So it seems that just not measuring a qubit, it should act as the same as the preparation, but from the other side. Yeah. So you should auto fix the qubits. What in theory I showed allows for much more powerful quantum computers, better stability, and in theory solving NP problems. Yes, so I think this is the most promising for practical two-way quantum computers. However, it needs help with somebody being expert in superconducting quantum computers to maybe to write some theoretical article analyzing this kind of situations. Yeah? So what happens if we perform the impulse for state preparation not at the beginning but at the end? And the other question, what happens if qubits which are not measured? Yes, but they so naively they just radiate energy, but looking from CPT perspective, these are ground states entering unitary evolution. Yeah, so it should act the same as state preparation if you believe in CPT symmetry. So entropy against CPT symmetry, there is growth of entropy. However, here we work with very low temperature, so to avoid growth of entropy, so we should be able to assume that there is no growth of entropy. Okay, here is another approach for two-way quantum computers. So I will talk more about it, about photonic approaches especially. So generally, you have electromagnetism and hydrodynamics, which are governed by very similar equations, especially for hydrodynamics without viscosity, the superfluidity. So there should be this analogy that behaves quite similarly. And we for optical processes, we have many opposite processes. Yeah, so we have optical heating, optical cooling. There is pushing, there is also pulling. There are tweezers which both pulse and push optical. And finally, there is a radiation vector, which radiation pressure, which is a vector. So it can be toward a surface, it's positive, but in theory, it can be also outward a surface. Yeah, so radiation pressure can be also negative. So I will show some other potential applications of negative radiation pressure. So not only just pulling, but there are many other interesting applications. So let's think about these simple situations that we can control flow of information from both directions. So we have this two-way control of the process. Yeah. So for example, for electronic chip with battery, this battery acts as a pump for the electrons. Yes, it both pushes the electrons with kind of positive pressure, no, with potential, and pulls electrons from the other side. Very similar is this microfluidic situation that we have a pump which pushes with positive pressure and pulls with negative pressure. Yeah, so having a quantum computer based on superfluid, and they are started making them. If you just connect this as such microfluidic quantum computer to a pump, we will get two-way quantum computer. Yeah, so this is another approach. But that having microfluidic quantum computer, it is very easy to get two-way quantum computer. So now using this similarity between electromagnetism and hydrodynamics, we should be able to take it also to the microwaves. Yeah, so but I haven't heard of microwave quantum computers, but maybe it can be done. But finally, the most practical would be photon-based two-way quantum computers. But we need pump for photons. So the question is how to build a pump for photons. And seems that ring laser should act like this. So ring laser enforces photon circulation inside. Yeah, so now we have circulation of photon inside, and so we inject these photons here into this photonic chip. Yes, and the state preparation is done with injection of photons into the photonic chip. But from perspective of CPT symmetry, the same situation injects the photons from the opposite side. Yeah, so we kind of both push the photons with positive radiation pressure and pulse with negative radiation pressure on the opposite in the CPT perspective. Yeah, so that's the main view. So for photonic quantum computers, I hope just connecting them with this to this ring laser should allow to make two-way quantum computers. However, it needs collaboration with a company which working with photonic quantum computers. Maybe classically it should be also very interesting. A photonic computer. And the final, the fourth example is there are these topological quantum computers which are growing in popularity. So maybe they will not work, but they are very time symmetric. They literally are trajectories in space time, and the usually they say that they measure by annihilate pairs, but we can annihilate with chosen. So I think we can influence this situation. So to influence the not only anchor the trajectories in the past, but also here. Yeah, it looks very symmetric. So probably there are very simple to make two-way quantum computers out of them. Okay, so we have this. So we have this team. So generally, we believe that physics is CPT symmetric, especially quantum field theory. And so, but in applications, this is a very powerful property of physics. But do you know any real applications? So I think there are many applications like this one. This is one of them. I also mentioned a different one, but I think there should be many applications of this symmetry, which is known, which is taken as just some strange property, but it's a very powerful property. I think we should try to apply in real life situations. Okay, so we have this the team this for X Prize. So if somebody is interested and could really help here, you can still join and maybe win $1 million with us. Then we have some interest. There are a few articles I will mention further. And so, but the most interesting question is, could we realize it? So, but it needs collaboration with experimental people. For example, experts in superconducting quantum computers. I think this is like the closest direction, or with the photonic quantum computers. So there are these two ways. So if you or know somebody who might help you, we would gladly collaborate to get essential improvements. So I'm talking about now. Okay, let's look at a few slides about theory, and then I will go back to some physics, more physics arguments. So we can think about two-way quantum computer as post-selected one-way quantum computer, but a higher success rate. So what do I mean? So let's think about standard quantum computer leads to some final density matrix, and usually then we just measure them. So let's think about just preparation, evolution, and now we got some final density matrix. We would just measure. So just measuring them in one quantum computer, we just use this formula, as you probably well know. And then we can think about post-selected one-way quantum computer. Yeah, so it does not just measure, but also would like to post-select. So there is some condition C, and it would like to post-select this condition that some qubits have some fixed values. Yeah, so we measure all the qubits. So and the original n qubits plus this m qubits for this condition. So we get this probability at the top. But now we have this post-selection, so we can divide by probability of this condition. So here is the final formula. This post-selected one-way quantum computer. So we have this additional post-selection, yes, in comparison to the standard one-way quantum computer. So, however, the problem with post-selection is that this PC can be very small. In practice, it usually drops exponentially with the number of post-selected qubits. Yeah, so that's the problem. So in postparation, we instead of performing this selection, we try to enforce, we project this condition qubit. So again, we would like to use this projection literally, so enforce the values. And doing so, in theory, we get the same formula. Yes, so the results of these two-way quantum computers should be the same as for one-way quantum computers. The difference is that post-selected has this success rate, which is exponentially developing. For two-way quantum computers, in theory, you should get nearly one probability of success. Yes, so we should get, in theory, up to exponential speed up in comparison to standard one-way quantum computer. And I will further talk about NP problems, in theory, being able to solve. And from the other side, there are these Scott Aronson's post-BQP, which add post-selection to BQP. And it is known to contain NP. So I think there are no doubts that having post-selection and not having this penalty, this very low success rate, you should be able to attack NP problems with quantum computers. Yeah. So being able having this post-paration, this stronger version of post-selection, just the same as preparation, but done at the end instead of at the beginning, we should be able to get these attack NP problems. Okay, so let's see some practical attack of NP problems. Yeah, so in NP problems, we would like to find input which satisfies some polynomial time verifier. Yeah, so there is some property you would like to satisfy, and the question is to find the input which satisfies them. The problem is that the number of inputs is exponentially large. Yeah, so polynomial is cheap, but there is a huge number of inputs. There is no difficult to find the proper input. And there are these NP-complete problems like TRISAT, so that there are NP-complete that solving one of them in polynomial time. In theory, we would be able to solve all of them in polynomial time. Yeah, so we can focus on one of them, and if successful in polynomial time, you should be able to solve all the remaining. So if so, there are many consequences of being solved NP problems, like much more powerful cipher breakers. So this is one of the dangerous consequences if successful and two-way quantum computers. From the other side, from positive side, there are global optimizers that, for example, we have a function and you'd like to find global minimum of this function, like the best configuration of chemical molecules for a given drug, for example. So to do it, we could ask, is there a value of this function below some threshold, and ask it for multiple threshold, and you could find the optimal threshold finally. Yeah. So with NP solvers, the most powerful application I think would be global optimizers. And also I further mentioned that in theory they also allow for better correction, better stability to quantum computers. So having this additional post-paration operation here, yes. So let's go back to this TRISAT problem. So in TRISAT problem, you have these clauses, these alternatives of three variables, and some of them can be negated. Yeah. So and you would like to find the values, 0, 1s, Boolean values, such that all these clauses are satisfied. Yes. So let's think how to do it with quantum computer with post-paration. So we could prepare quantum superposition of all the inputs to the power n inputs, and then calculate this verifier, like these clauses. And then instead of measuring them, you would like to enforce them to 1. Yes, so you'd like to make this preparation, but at the end. So it could be done with post-selection. However, doing it with post-selection, we get this exponential drop of success probability of post-selection. Yeah? So it would be much better to have to be able to enforce them. So being able to enforce them, then you can just measure the value and you should get the X. Yes. So in theory, it's relatively simple. So it's quite similar to Shor algorithm. So in Shor algorithm, we also prepare this exponential number of inputs, calculate classical function with power, and instead of post-paration, perform the measurement. And then some quantum Fourier transform and getting some hint for the factorization problem. So here we need to replace this measurement with enforcing, with this post-paration. Yeah? So we'd like to enforce that the superposition literally has the satisfies all these alternatives, for example. Okay, so this is idealized situation. So let's think what can happen for practical implementation. So the main problem is that some of these alternatives can be wrong. So it can lie. This computer could lie. So could not. So there is noise, and there are different values. So thinking about this kind of, so in this case, instead of having just the solution to our NP problem, we have this ensemble with epsilon being this probability of one clause being wrong. So there can be one clause wrong, two clauses wrong, three, and so on. So, but the number grows exponentially usually here. So to be able to be certain that we can solve any problems, in fact we need very low epsilons. So the question is, can we get exponential? Can we reduce this epsilon exponentially? So this is a very difficult question. So generally working on copies, we should have powers of this epsilon, so should improve it. So in theory, it should be doable. So the question is, do we need some error correction to improve this epsilon to this exponentially small? So there could be standard approaches, but two-way quantum computer allows for some better mechanisms for error correction. For example, we could make this kind of gadget. Yeah. So what it does, it enforces that these two qubits to be equal. Yeah. So this is literally equalizer. Yeah. So the gadget which enforces two qubits to be equal. So in standard quantum computer, you would measure here. Here you can enforce it to 0. Yes, to enforce that these two are equal. So you could make the copies by regularly equalizing the two qubits to stabilize the flow of information to try to enforce that these J qubits are equal. Yeah, so we could make many this equalizer to try to work simultaneously on these J copies of each qubit to try to get down to this epsilon to exponentially small. Yeah, so in theory it should work. Yeah, so the question is, could we do it right? So I think it should be doable to overcome imperfections to solve NP problems, having even not perfect this postparation. And this the example this gadget is example of this general approach of better error correction. So this is enforcing that these two qubits are 0 0 or 1 1. Yeah. So we can say that this is a code book. And so code book in error correction classical also is there are some bit sequences which are far from each other in Hamming distance. So we could use a larger code book, so some better error correction, and again enforcing syndrome to 0. So enforcing that we only use these code words. Yeah. So we could make error quantum computer which tries to make on ensembles only of code words of some code book. So they are very far away, so there is chance for better stability, error correction. Okay, so another view on better stability error correction is approached by Grzegorz Lusta to Groover's algorithm. So here is his view, and now instead of measurement, he makes this postparation here and compares this Groover's algorithm with standard one and tests for various noise models. And you can see that the blue line is for two-way quantum computer. So you can see that even with the noise level, so the blue line behaves much better. So indeed, this postparation allows to improve the stability of quantum algorithms. Yeah. So there are many arguments that we can have better error correction. This gadget, this equalizer gadget, for example, maybe also for more complicated error correction code books, and that we can also improve stability. So there is having this postparation, we could essentially improve quantum computers. So I think that it could be very soon practical. While now they are not really. Yes. So I think this is if getting it forward, this should be very large speed up for the quantum development of quantum computer field. Okay, so another question. So could we validate the no cloning theorem? And turns out that we cannot. So so we cannot like make an attack on BBH-4 by cloning. So this is very similar to proof to standard no cloning theorem. So we assume that we have this cloning operator, which additionally has this F, this additional qubits to be measured, to be post selected on post paired on. So assuming that there is this cloning operator, we can standard way get to contradiction, so there cannot be this cloning operator. Yeah, so no cloning theorem is still true for two-way quantum computers and for post-selection. Okay, so let's go back to physics. I'm trying to give you more arguments that it should be doable, but it's not simple for experimental perspective. So it needs help from experimentalists, especially, and experts. So let's go back to the CPT symmetry. So generally, physicists believe that equations governing physics should be the same if looking at the system from perspective of the CPT perspective, CPT symmetry. Yes, so that we change time. This is most important. That we switch time to the negative. Yes, so that evolving time toward negative time, physics should work the same. Parity and changing charges. Yes, so this is extremely powerful property which should have practical also consequences, but I haven't had any practical applications, and two-way quantum computers is one of such proposal of really practical application of CPT symmetry. Yeah, so it is crucial for modern physics. Yeah, there is Schwinger's theorem that Lorentz invariant quantum field theory with Hamiltonian has to satisfy the CPT symmetry. Yeah, so if it would be violated, then most of physics would be wrong. So we have to change the entire physics also. But maybe this kind of experiments tries to build such two-way quantum computer will say that there is some wrong. So maybe we could get some violation of CPT symmetry trying to build this two-way quantum computer and with different applications I mentioned in a moment. Okay, so we believe that in equations governing physics they are symmetric, also in time. So CPT. So one can say, but what about entropy growth? Yeah, but which clearly distinguish past and future. So generally the answer is very simple, that there can be equations. There can be that if equations are symmetric, the solution doesn't have to be symmetric. Yes, like this surface of lake. It is symmetric in equations, but if you throw a rock, the solution is not symmetric. Yeah, so there is no problem to have asymmetry in solution, but symmetry in equations. Yes. So and then I talked about now about some photonics laser applications. For example, that it naively we can only excite target with laser, but turns out that we can also de-excite, cause de-excitation of target with laser. And one of example applied is the STAT microscope. That in STAT microscope there are two lasers. So one laser excites these dots, the dot. The second laser causes de-excitation of the dot. So the final dot is very small. So this microscope gets better resolution. Yes. So this is a reminder that with laser we can not only excite but also de-excite. So this is this positive negative radiation pressure. So this is positive radiation pressure, and this is kind of this negative. And for example, in Rabi cycle, we have both. So now we go to Rabi cycle, which is, I think, is very thought-provoking, very simple looking, but very, I highly recommend thinking about it. So in Rabi cycle, we can, for example, laser and the target. Yes, and there is cyclic change. So this laser causes excitation of the target and de-excitation, de-excitation. Yes, so there is both. There are these two equations, symmetric emission and absorption, and here is the equation for this causing excitation. Yeah, so the laser increases the number of excited these N2 atoms at cost of these ground state atoms. And there is this symmetric, in CPT symmetric equation, which has the opposite, which increases the number of of ground state atom at cost of excited atom. So we can see that laser can cause both, yes, as like in this cell microscope, it can cause the excitation. So the question is, could we separate these two processes? So could we have a laser which causes only excitation or only de-excitation? So kind of having only positive radiation pressure or only negative radiation pressure. So I try to convince you a few ways to how to separate them. So the Rabi cycle is also very similar mathematically to these couplet resonators, like this couplet pendula, which are periodically exchange energy. Yeah, so one has large oscillation, then it exchanges energy with the second one. And we can also think about this hydrodynamical analog I have mentioned. That so could you get this situation in hydrodynamical? I think this is quite similar. That we have a water tank with semi-transparent wall. We have standing wave in this water tank and some particle outside. So this particle would go left and right because there would be a positive, negative momentum transfer to positive, negative radiation pressure. Yes. So cyclically again. Right, left, positive pressure, negative pressure, and so on. Yes. So yes, again, the radiation pressure can be positive or negative. Okay, so however, it turns out that many lasers have built-in this optical isolator, which forbids photons going left. Yeah, so here we needed photons going right, and photon goes left. However, most of lasers have optical isolator which forbids this going left. So why we would like this simple direct realization, what is allowed, for example, for microwaves, looking at in literature for Rabi oscillation with lasers, I have found two types of approaches. So one is this one, which adds resonator, additional resonator, and the second uses this Mach-Zehnder interferometer. So let's think about this the first one. So we have a laser with optical isolator and the resonator. Yes. So this laser is pumping this resonator, and the Rabi cycle is between the resonator and the atoms. Yes. So we can go around this optical isolator. And Mach-Zehnder is also very interesting. So we can see that while here the photons go left, right in the same path, it looks like the photons use the opposite paths. Yeah, so in go here and out go here, and in CPT perspective the opposite. Yeah, so this is interesting trick to go around this optical isolator inside the laser, I think. Okay, so let's think about this water hydrodynamical analog. So here is some liquid, and if we move an object in liquid toward right, then we create both positive pressure. We could push objects here, but also negative pressure. From CPT perspective, they are switched. Yes, and we can think about this wave, spheroidal wave behind the marine propeller. It carries energy, momentum, and angular momentum. So it resembles something in physics. So the photon also carries energy, momentum, and angular momentum. Yes. And if we reverse the direction of this marine propeller, then it would cause the opposite momentum and angular momentum. Yeah. So it would not push but pull. So this is positive pressure and this is negative pressure. So why not for electromagnetism? Yes. So and the best, I think, example is synchrotron radiation. So in synchrotron radiation, so now we go to electromagnetism. You have a charged particle traveling, for example, in this circle-like trajectory, and it creates these photons, synchrotron photons. So we can think that this is positive radiation pressure here. Yes, but believing in CPT symmetry, the same charge, opposite, is traveling this direction, reverse that direction. So it should also create photons, but now in this direction. However, these are photons in CPT perspective. So from our perspective, they would travel toward negative time. They would excite target toward our negative time. So for us, they should de-excite target. Yes, so they should cause the excitation of our target. Yes, it sounds strange, but if you think about these pictures and CPT symmetry, I don't know how to avoid these photons, these CPT photons, if you believe in CPT symmetry. I don't know. So if you know, let's discuss. So it should create this negative pressure here, negative radiation pressure. So could we observe it? So this is a very interesting question. Could we observe this negative radiation pressure, for example, from a pulsar? So I think we could. So let's think about standard telescope. So standard telescope has this detector which is often cooled and monitoring population. Yeah. So the photon from the, let's say, from synchrotron radiation in the pulsar will excite atoms in our detector. But if we build this pump detector telescope, again monitoring population, so now this negative radiation pressure should pull these photons. Yes, from our perspective, these are photons going from the detector toward this pulsar, but caused by the pulsar itself. So using this stimulated emission. So this is so standard telescope is focused on this equation, and this proposed pump sensor telescope would be focused on this equation. Yeah, so the pulsar should cause the excitation in this detector. So building such backward camera detector, we should be able to see not positive but negative radiation pressure from the target. So I think it would be very interesting to find some different sources of this negative radiation pressure. So one candidate is synchrotron radiation, but maybe there could be other astronomical very interesting objects which also should cause it. Okay, so let me mention briefly some different application. Yes,
Jarek,
yes, sure.
if I could ask a question in the previous
Yes,
slide, when you were talking about the negative pressure going the other direction, the thought that immediately came to mind is, aren't the magnets interacting with the electrons in a fashion that they're going to take up the negative? Isn't aren't the momentum issues going to be resolved through the magnets?
So this is the same trajectory, but only viewed from perspective of CPT symmetry. So you just reverse the trajectory. If you reverse the time, yeah. So you reverse the trajectory. So now again, you should have synchronous radiation if you believe in CPT symmetry of physics. Yeah. So the question should be the same, governing physics. So if they are producing photons here, why not here? And these photons, in CPT perspective, for us, from our perspective, are a negative radiation pressure because the excitation of our target. Those cause excitation, those cause de-excitation. So if somebody
Symmetry of what you're saying here, I'm kind of poking at it and saying are there other factors involved? But I hear what you're saying, and I think it's an intriguing argument. So that was all.
Yeah, so it would be extremely interesting to build this kind of reverse telescope, yes, which have pump detectors. So it's not simple to construct it, but I think it's so if you know somebody in space industry who could build kind of this kind of detector. So I thought so there are many ways to do it, but it's not simple. So it would need collaboration with somebody. Yeah, so it would be very interesting to check what you can see. So I think it should only see the synchrotron radiation. So for example, having this and a standard telescope, we should be able to distinguish thermal from synchrotron radiation from objects, for example. But so I think it would be very interesting to build this kind of telescope, but I don't know how to realize it. So if you know somebody, so we can discuss.
I just mentioned there is a physicist associated with Aharonov who has looked into some negative momentum issues with photons.
Awesome.
I'll have to find the link to you, but it's very intriguing.
Sure.
So
please email me if you know some materials. Please email me or contact. Sure, I will discuss and read and contact some persons who might be interested. Sure.
Okay, I'll be sure to send you the reference. It's a very interesting paper.
Oh, thank you. I will discuss. So maybe let me show a different application of very similar. So again, this standard cameras, this backward camera, but for application for medical application. So yes, so if having this source of negative radiation pressure, so one approach is the synchrotron radiation. I think a simpler approach is this link laser, but still it's not simple to get access to this kind of lasers. But so think about this laser. So let's think about CT scanner, computer tomography scanner. Yes, so we have some source of photons. You have the detector, and you have some, let's say, a patient, a human body in the middle, and the human body, let's say, subtracts this integral of ground state atoms on the go. Yeah, so this is standard measurement of absorption coefficient, which can be used, for example, for 3D maps of absorption coefficient in computer tomography. But let's look at CPT symmetry of this picture. So you have to reverse the photon trajectory here, and again, you need to excite the target. Yeah, so here you have this source of negative radiation pressure. Here you have positive, and here you need to excite the target. So you have this. You need this sensor with pumped atoms. It's quite difficult to construct. both also this one. So doing so, you should be able to calculate not absorption coefficient, but emission coefficient. So why it is more interesting? Because the number of excited atoms is usually orders of magnitude smaller than ground state atoms. So this one should have much better transparency. So this photonic should easily go through human body if being able to construct something like that. Yes, and you should be able to make 3D maps of excited molecules in given frequency in human body, for example. And there are many molecules which are excited in human body. For example, these autoluminescent molecules, which are excited through biochemistry of life, like NHDH. So I think with this kind of CT scanner of emission coefficient, you should be able to do color Röntgen kind of, so color as multispectral map, very accurate, because these are photons, lasers, so and relatively cheap, I think, and not ionizing radiation, so it should be much healthier than standard CT. I think this is very promising, but there are two difficulties. One there is this pump detector, and the second is a source of negative radiation pressure. But having both, I think we could get much better computer tomography scanners.
Sorry to interrupt here.
Sure.
I just wonder if what you talk about, this excitation and de-excitation, is there any similarity with sound propagation, where we have sound which causes no noise, and the engineers, they apply anti-sound, which basically is an opposite, or in terms of phasing, to cancel the sound.
So I think sound is similar to hydrodynamics, yes. And for hydrodynamics, there are very similar equations. So okay, so here are some similarity between thermodynamics and hydrodynamics. So especially for superfluid, the equations are very similar. And what you have mentioned is, I think, this sphere-like wave behind marine propeller. Yes, you can just reverse the direction of this marine propeller, and you get the positive pressure, you get negative pressure. So I think you could also do it with sound. You should get sound.
Yeah, thank you. So it's a phasing issue, basically, different phasing.
Yeah. So yes, reversing this direction here. So also performing the time symmetry of the process producing the sound, this wave. Yes. So I think, yes, sure. Yes, so they are very similar. Electromagnetics, hydrodynamics, this acoustics should be very similar mathematically. So it should be all of them should be transferable. But for photons, I think it's much more convenient. Especially you will not, I think, get maybe some ultrasound scanner which goes through the body. Maybe also is worth considering here. Instead of pushing the wave, to try to pull the wave to the body and ask how much of the energy was held by the body, yes, absorbed by the body. What I think has very different transparency. So yes, so usually this can have better transparency. So while standard light goes like 1 or 2 centimeters to the body, this might go to the entire body, I think. I hope. So I think it's very promising. But we need to construct this pump detector and negative radiation source. Okay, so we wanted to make some simpler tests, but we were not able to get equipment or success. So there are this something similar is called amplified spontaneous emission in fiber optics. So there are for example, this kind of article that you have a laser here. Here you have excited atoms of erbium, and this laser literally amplifies emission from photons toward the left. So pulse photons, literally pulse photons. However, trying to realize it, we were not so successful. But this is one simple way to try to realize it. But so like here, that you have laser, and standard laser has optical isolator toward right, only allowing to push, not pull. So there are problems with Rabi cycle, for example, because of this optical isolator. So maybe just to switch this optical isolator from CPT perspective, you get similar sound. But we are not able to make it work with simple diode lasers. So maybe some better lasers could do it. But the much more promising is this ring laser, which literally enforces circulation. So from CPT, so now it causes excitation of this target. But from CPT perspective, you reverse the circulation of photons. So you should cause excitation of this target. So from our perspective, the excitation of this target. Yeah, so it should be this negative radiation pressure source. So I think this is a very promising approach. If this will not work, the synchrotron radiation is the final chance, but it is much more difficult to access and yeah. So for synchrotron radiation, we have a free electron laser. You have charge traveling like here, so it produces photons and excites target here. But from CPT perspective, the charges are traveling the opposite direction, so it should excite this target. So from our perspective, it should cause its excitation. Yeah. So there are these two equations. We switch them in CPT perspective, but it should create also this negative radiation pressure. So it would be great to observe it. So for example, in some synchrotron or free electron laser, so I'm talking with one of the synchrotrons here. So it's like here is Solaris. However, the problem is to access this negative radiation pressure. So it is built so densely that you cannot access it. Yeah. So it would need changing the structure. So it's very difficult to in the real realization to access this. However, if you have bendy magnets, this is a nice place to access this kind of radiation, this backward radiation, negative radiation pressure. So if you know somebody, I will discuss collaborating on this. Okay, so maybe one more, some more controversial. I don't know. So okay, some philosophical one slide. So generally, the question is that using this CPT symmetry requires some proper philosophy of time. So naively, we use this presentis, that there is some current situation, it evolves in time. So in theory, it is equivalent with so-called eternalized block universe. We have, there is four-dimensional solution, and we're just traveling through it. However, solutions formed originally with one of them have different properties. So I could talk about it, but generally, if you want to violate Bell inequalities, you cannot do it with presentis, what is well known. But if you go to eternalize, then it's not a problem. You get the Born rules, the Bell violation. Literally, you get ensemble path ensembles. If you use ensembles toward one direction, you get first power. If you use full ensembles, you get second power. You get the Born rule. You can violate Bell inequalities. And here you have this if you use general relativity or quantum field theories, all of them are based on this eternalized block universe philosophy of time, that you work on four-dimensional scenarios. You don't say that the space-time is developing. No, space-time already is and satisfies the equation, the Einstein's equations. So also in quantum field theory, you work on four-dimensional scenarios, Feynman diagrams. So modern physics requires this philosophy of time, and it allows for general relativity allows, for example, these wormholes in theory which are non-orientable. So this is just a thought experiment, but in theory allowed for general relativity. That you have wormhole looking like this, so it's non-orientable. That if you travel to this wormhole, it would switch the time to negative time. So yes, it sounds crazy, but general relativity in theory allows for this kind of solution. So if you have a rocket traveling through it, your one quantum computer would be reversed. So yes, so this measurement would become pre-measurement. The preparation would become post-preparation. The two equation would switch. Simulated emission and absorption equation would switch. Yes, so again, general relativity allows another way to realize this post-paration, but it's more crazy. So, but that's another theoretical way. Okay, let me finish. So I think there are the most promising ways to realize to a quantum computer. One is the superconducting, because using low temperature as state preparation, it is the same in CPT perspective. Yes, temperature doesn't change. So it should be still low temperature. If you can use it for state preparation, you can also use it for post-preparation. So but I think it needs some low-level access to these quantum computers, so to be sure that it does exactly what we need and to well understood the situation. So it needs collaboration with some specialists in superconducting quantum computers. So we would gladly collaborate. So feel invited to our team to win $1 million from X Prize. Another approach is silicon quantum dots, that if you have impulse to tunnel, we can reverse this impulse, no problem, to tunnel back. So from CPT perspective, you get preparation. Another approaches are photonic quantum computers, yes. So like here, this ring laser, I think should do it. So from CPT perspective, you reverse the photon trajectory, you should reverse the two pressures, positive pressure, negative pressure, positive, negative. Yeah. So there are these three most promising ways to get to a quantum computers. However, all of them are very difficult experimentally. So if you know somebody, you would rather collaborate. Okay, so that's the end. Thank you for listening. I will gladly discuss, collaborate if you know somebody.
Okay, great. Thank you.
you.
Thanks, Jarek, for the presentation. Yeah, let's see if there are some questions. So,
Okay, there
I
is
have a
something.
question.
Barry. Yes,
Sure,
yes,
sure.
please.
Please unmute and
Yeah,
ask.
thank you for your presentation.
Okay.
Oh, can you hear me?
Yes.
Yes.
Yeah, thank you for your presentation. I came to I found an article where they were talking about the possibilities of building quantum computers with with a magnet. They are trying to adapt the system of gate and a remote controller for gate in cars. And my problem is, how will this make?
So
Do
generally,
you know if this method will be effective, and how this?
so I don't
Go
know. I
ahead.
don't know the technology. You'd have to send me an article so I could think about it. But generally, every technology might need some different tricks to get to a quantum computers. But you need to take a closer look at what's happening in the state preparation and try to make a reverse process. Yeah. So for example, if state preparation is low temperature, then reverse is the same. Yes. If state preparation is impulse, then just reverse the shape of this impulse. If state preparation is injection of photons with positive pressure, you need to apply negative pressure. Yeah, so there are these three basic tricks to reverse state preparation process. Yeah, so maybe one of them could be used in this technique, but I haven't seen it, so we can discuss.
And
But
the last
generally,
question.
you have to look at the state preparation process. If it often it's
Okay.
just lower temperature, so should be the same.
Okay, thank you. And the last question: how far are we with building a real quantum computer? Because right now, people are just using classical computer, and it has been proved that most of the algorithm can be applied in classical computers.
So generally,
So talking about the quantum computers.
So there are many approaches, like hundreds on the world. But generally, hopefully, this kind of approach can be applied in standard technique. So like for example, if you have photonic quantum computer, hopefully just connecting into with ring laser into a loop should allow for two-way quantum computer. If you have superconducting quantum computer, I think maybe just keeping the measurement might allow for two-way quantum computers. For silicon quantum dots, you have some impulse for state preparation, just reverse the impulse at the end, and hopefully you should get two-way quantum computer. So this is so hopefully current technologies should allow for two-way quantum computers, but so I'm not entering into details of entire gates of the technology, but only suggest to try to upgrade the current quantum computers to get better error correction and in theory allows to attack NP problems.
And so right now, are we able to do quantum computing without using a classical computer?
So as to my knowledge, I don't know any real practical application of currently of quantum computers, but if being able to apply this upgrade, this two-way quantum computer, like one of these three approaches, they should be much faster practical. Both error correction improves and allows to attack anti problems. So I think if being able to make it work, any of these approaches, they will be practical very fast.
Thank you so much.
I had a question.
Sure.
So this is just on the theoretical side for the
Yeah.
experiment. So whatever setup you have for excitation that you're doing, it would make sense to me to have the same exact setup on the target, but in the opposite direction for the push-pull. If you try to do a switch on the same system to do that, there's too many delays, there's errors, there's all sorts of things. And then that would open up the whole issue of like quantum engineering, where I have to go in like a parametric filter to filter out noise and find it and all of that. But the two-way system, you've turned them both on and you calibrate it. So once they cancel each other out, it's at zero. And then and then you can start doing the tests that way. I know.
Yes, so technically photonic might be very difficult. Yes, I agree. So, but generally you have resonators. Usually you just have resonators here and photonic chip and measurement, and here you have two resonators and put the photonic chip between the two coupled resonators. So intuitively, even classical, I think it would be better. But yes, there are problems. It can be continuous wave, can be impulse. If working with impulse, it has that you have to include the delay.
And then it makes me think of too, to possibly look at some of the latest advancements with MRIs and how they're using, magnetic resonant imaging, because there's a lot of advancements in that area that may be useful in some things that they're doing. That's just an idea too.
Sure. I don't know. Yeah. Thank you. So if you know some article, which could be valuable for me, I've already discussed, but I have to take a look. And generally for experimental, we need collaboration with somebody working in this kind of approaches. Yeah. So it's very difficult to. You are independent team and need collaboration with some experts in one of these fields.
Right. Do we have more questions to Jarek?
Some chat questions. Okay, so there is some long discussion called slides. Thank you, of Shalom.
Yeah, there is a question. Do these two-way quantum computers require the Hamiltonian of the system, of the systems to be Hermitian?
So generally, we assume that the unitary evolution is the same. We only modify the state preparation, maybe also measurement. Yeah. So here we don't touch the unitary evolution here. Only try to change so we can assume standard quantum computer which is unitary, only try to modify the boundary conditions. It's like adding this additional laser here, for example. So everything else is the same.
Mhm. All right. Do we have more questions?
Sorry, I know it's so. Negative mass particles. So yes, I have some.
Just another question is,
Yeah.
I just wonder, so maybe that I missed it, you might have mentioned at the beginning. This work that you've done is just pure theoretical framework.
Yeah, so
Has been there any experimental work to see a feasibility of this theory?
So the experimental needs collaboration with experts working in these technologies. So we are open to this kind of collaboration, but we don't have any way to do it ourselves. Yeah. So yeah. So there are. So if you know somebody who might be interested, we'll discuss. But we don't have access to this kind of experimental stuff to test it.
Yeah, thank you.
Thank you.
Mhm. Okay. Do we have more questions? Okay, so I think we can finish for today. So Jarek, thanks once again for the great presentation, and yeah, as Jarek said, he's open for collaboration, and we've also submitted this idea to the X Prize competition. So we are also looking for collaborators.
Also, the
Mhm.
Discord, if you would like to discuss with us, there is like 100 persons on this Discord. We can discuss and collaborate there. So please email us. And there is X prize, so we can win $1 million, but probably it requires some experimental confirmation, but for which we need a collaboration. So especially people experts in one of these technologies are welcome to our team. So to try to win there.
Mhm. Okay, I think that's all for today. So thanks, Jarek, once again. Thanks
Thank
everyone
you.
for coming, for joining, for the questions.
Can I ask very informal question?
Yes,
Sure.
yes, please, Itamar.
First of all, I'm admiring all the physics that you're doing here. It's quite amazing. And sorry I came late, so I can't relate much to the
Mhm.
beautiful knowledge that you described here. But my wonder is, with all these nice theoretical developments, can you, or maybe you did, face or try to solve the open problems in quantum computing, for example, error correction code and other challenges that are in quantum computing today?
So yeah, this addition of this postparation in theory allows to improve error correction. For example, this is one approach that it allows for this equalizer gadget, which enforces two qubits to be equal. Yeah, so in standard quantum recursion, you'd measure here, and here you can literally enforce them to be equal. So you can work on multiple copies of the same qubit, what should allow for better error correction. So this is one direction. So error correction should be much better for two-way quantum computers. And the other direction is that testing errors, it literally stabilize the flow of information. So you can control of the system from both directions. So what allows you to stabilize the system. So in theory, it should work much better. So for different error types, literally the two-way quantum computers behaves much better. So you have much better control. So let's think about this like here. So here you just inject the photons into the chip and watch what's going out. And here you additionally try to control the from two directions. So you try to control the flow to the chip from both directions. So it is it allows you to get better stability of the flow. Yes, you get better control, two-way control of the flow of the information through your chip. So in theory, it should be much better, but to get it right, we would need to collaboration with some people, some experts in these technologies.
Okay, how about dealing with P versus NP?
Yes. So in theory, it allows to solve this upgrade. In theory, allows to solve NP problems. So here is such approach. So for example, like in short algorithm, you start with superposition of all 2 to the power n inputs. Then instead of in short, you measure calculate these powers and measure them. Here you, for example, calculate these alternatives of three variables in TSAT. So imagine, so here is your NP verifier, like TSAT alternatives. And now instead of measuring, you'd like to enforce them to one. So you'd like all these alternatives to be true, or your verifier to be true. What should restrict your assembler to only satisfying this NP problem? So you just measure them, and you should get the solution to your NP problem. So yes, so in theory, two-way quantum computers not only improves on stability error correction, but also in theory also attack problems. So this is a very powerful possibility. So I think so if getting it work, so I think this we could, for example, make global optimizers, like in a moment finding the best molecule for given task for drug design or something. Yes. So finally, these are much more powerful than standard one computers in theory. So not BQP problems, but post BQP.
Okay, so with all this achievement in theoretical, powerful approach that you describe, is it possible to guide the people who look for new materials or people who deal with a large population of cells in biology? Like I'm trying to take this amazing theoretical framework that you build to use it for pending practical problems that are faced by actually humanity.
So having NP solvers, you have global optimizers. You have some very complex function, and you can find its global minimum. So yes, so all these optimization problems probably could be solved. So if you have polynomial time verifier, so if you can evaluate the solution in polynomial time, then you can find the best input. So for example, algorithm search, for example. So imagine that you like that your verifier checks that if given number of steps, your algorithm solves this problem, and now find the best algorithm which in given number of steps solve this problem, for example, or cipher breaking. So in theory, having NP solver, you can solve nearly all ciphers break. So for us, symmetric encryption, your verifier could be using given cryptographic key and to decrypt some initial part of your file. Do you get noise or not? So only the proper key will give you not noise, and the remaining will give you noise. So you can the verifier could use the key to decrypt first part of the file and check check its entropy. If entropy is low, then it's proper key. If it's large, then it's wrong key. So you can turn it into NP problem. So I think most of ciphers could be broken if having two-way quantum computers. So this is the dangerous part of two-way quantum computers.
This is very beautiful. Thank you so much for your answers and your talk. Thank you.
Thank you.
Jarek?
Yes, sure.
I was just wondering if you frequently there are calls for proposals from the U.S. Department of Defense that cover a lot of the same type of technology areas that you're talking here. There's certainly a lot of interest in quantum computing, ongoing interest. To access those, you would need an American primary or something to do that. And again, this is all, who knows we're in chaos.
I know.
We're in absolute chaos. We don't know what's going to happen on any of it. But traditionally, many of the groups have a primary thing where if you have a U.S. primary, you could get access. But some of your stuff just really sounds like it could be of interest to some of those proposals that you could just look around in the internet and actually in many cases find that. A lot of times people don't realize they can just look in the internet and find some of these.
But they are for Americans, and now they are all frozen, if I properly heard. So generally, but if some American would like to collaborate on that, I probably we could do it together. But personally, I cannot. I'm not American.
Right, and that's what I'm wondering if there's some. You don't have any particular context existing like with any of the national labs or anything.
So I'm just university. That's all. So I'm.
Yeah. It's yeah. I wish I was still more connected with some of that of what's going on. And like I say, also it's pretty chaotic right now. But just to put that in, I think your emphasis on CPT is really good. One of my big problems with the whole Deutsch approach to quantum computing is that it just hasn't gone anywhere. I mean, I've watched that for decades, and whereas the CPT, that to me is just a really solid. You're getting a really solid physics with that. So
so that's negative radiation pressure. So we think only about positive radiation pressure, but there should be also negative. The question is how to get it. Synchrotron radiation should be one of them.
Yeah,
there are more.
So that's why I think you this is intriguing stuff, and I hope this gets a chance to get explored more experimentally.
Yeah. So if you know somebody, I will really
And
collaborate. But
I will, yeah, like I say, I'm
okay.
disconnected
Hey,
in multiple ways, but
hi, Jared. Yeah, how can I connect with you?
So there is email. If you just write Jarek, my name Jarek Duda as my Jarek Duda. So you find my webpage or Wikipedia or something.
I will definitely ask around this.
Okay.
I'm in a different area, on the research side right now, and this is of interest to me. If I pursue this PhD, this would be some of the areas I want to do, but I am on a different side of it with, generative AI and a lot of like trust evolving thing. There's a lot going on that space, but I will speak to people because this is kind of an area that I'm connected to some people that may be doing work in this area that I can speak with, but it's definitely not like I'm one-on-one working on this type of area at this moment. But I am very interested. So I will find
Sure,
out
sure. If you know somebody, I will really discuss. I can give a talk somewhere, or so just contact me. Yeah, sure.
Perfect. Thank you.
Thank you.
Jarek, can I share your Gmail address here on the chat?
Sure, sure. But if you just write Jarek Duda, there are
Yeah.
into search, you can find
Yes.
me.
So actually, I didn't tell it at the beginning, but Jarek is already quite a famous researcher. So there is a Wikipedia website about him and the invention of the ANS algorithm that is for.
So probably your data is written with my NS. So
Yes, so it's an
it's
algorithm for data compression based on entropy coding method called asymmetric numeral systems, and it's currently used by companies like Apple, Facebook, Google. So yes, Jarek is quite famous researcher already.
Jarek is one of the best algorithmics, I can't pronounce the word, in the world. Jarek, you've done stuff I haven't seen from anybody, so it's just amazing. And hopefully that could be some leverage in some of this other work in that too, because I just have the utmost respect for what you've done in algorithms.
Thank you. So yeah, so it would be great to move forward this physics stuff.
Yeah. Great. Thanks. Do we have more questions or comments?
Possible to show.
Yeah, I know. If could John Bush, sure, I know them. Yeah. I also work in this direction. So this is different stuff, but yes, I will discuss. So the dynamical models of particles, so liquid crystal. So yeah, so there is a lot of similarity between the hydrodynamics, these liquid crystals and particle physics, and I'm also working in this direction. So if somebody is interested, I will discuss.
Okay. Do we have more comments or questions? If not, then
There was some paper that you showed a few minutes ago. I think, Pavel, you showed it as a reference. Like 2 minutes ago, there was a paper that you showed.
I don't know.
paper.
Not this one.
Jarek, because you were, I think that only you were sharing the screen, so maybe you remember maybe this one.
So
Yeah, okay.
this one.
Thank you.
That was my fault. I put that in there. That was the paper I was referencing.
Sure. I will take a look. Yeah, sure.
Yeah, that has to do with negative mass on low energy linear momentum situations, but it's a very interesting paper. And an associate of Haronoff, who is still making papers. I'm not sure how old Dr. Haronoff is.
I have a mailing list, Nature of Time, with Arechuka and Avshalom. If somebody's interested, I can add you. Okay, so thank you very much. So please contact me if something I'm gonna discuss, collaborate in this topic. So especially if knowing some experts in one of these fields or maybe. So I think also this one, like building this telescope with pump detector, I think it will be extremely interesting. For example, to build this CAT scanner with much better transparency and with multispectral, you should be able to make 3D maps of these molecules in the body. I think should be doable. So I think much better medical scanners without ionizing radiation. But it needs these pump detectors and source of negative radiation pressure.
Mhm. Okay, last chance to ask a question. So actually, Jarek, I've also forwarded to you a message that I just received from Mary, so we can check it on Discord later.
Sure. Okay.
Good. Helen, I think we can stop recording for today.
Yeah.
Okay.
So we have this Discord. So if somebody's interested, so we have like 80%. So we can discuss also there.
I can also share a link to the Discord.
Sure.
Jarek, can I do it?
Sure.
Mm-hmm. All right. Let me just paste it here on the chat.
Jarek, I'm going to be departing, but thanks again for the talk. Great talk.
Thanks. See you
Thank
next
you.
time. Thanks.
Yes, thanks everyone. Thanks for joining, and we hope to see you next time in 2
Have a
weeks from
good
now.
weekend.
Have a good weekend.
Thank you.